Okay, yesterday we learned about the quadratic formula. What I want to do right now is show you how we can get the quadratic formula. We're going to derive the quadratic formula. So here's our quadratic equation. The general quadratic equation with variables in place of the coefficients and constant. So ax squared plus bx plus c. And what I'm going to do is I'm going to solve this generic equation, and that's where a formula comes from. That's where all formulas come from, is solving some generic situation. We're going to solve this, and I'm going to choose the method of completing the square to solve this. I know I want to complete the square, and as opposed to some other method, because completing the square always works, whereas factoring and graphing do not always work. So that's why we're going to choose to solve this by, this is how we get the quadratic formula. So I can't use the quadratic formula to get the quadratic formula. So I'll show where it comes from. So to complete the square, you may notice that there is a leading coefficient we'll have to get rid of, but let me first of all just get rid of the c. This is explaining where we got yesterday's formula from. It's showing how to get it. It's worth knowing, but it's not something you're going to have to do regularly. So first thing I'm going to do is move that c term out of there. I know I don't really care about that right now. I also have to factor out the a. Now, because the middle term did not have an a in it, when I take b and divide b by a, it doesn't simplify, it becomes the fraction b over a. Now, if we're completing the square, we have to figure out what it is that I put there in the parentheses. Hopefully you remember the rule that you take whatever the middle term is, the linear coefficient, and we cut it in half. So I'm going to have to take the b over a, cut it in half, or sorry, I wrote b over 2. I meant to say b over a. Cut it in half, so I'm going to multiply by half, and then we're going to have to square that whole thing. So when you take b over a and do half of it, we end up with b over 2a. But I have to square that. When I square the numerator, I get b squared. When I square the denominator, I get 4a squared. If I added that on the left side, what is it that I add on the right side? We have to remember there was a coefficient in front of that parentheses, so I didn't just add b squared plus over 4a squared, I added that b squared over 4a squared times the a that was out front. When you take b squared over 4a squared times a, we end up with b squared over 4a. Because the a will cancel out with one of the a's in the denominator. Now I can factor our perfect square. I would like a common denominator on the right side. I'm going to actually switch the order of these two fractions. So I'm going to leave the b squared. I'm going to move it first, b squared over 4a. And then instead of minus c, I need a common denominator. So it'd have to be minus 4 times a times c. just made a common denominator. So instead of c over 1, I wanted it to be a 4a for a denominator, so I had to multiply n 4a to the top and the bottom. Oops. So it was a c up there, and I multiplied it by 4 times a, so 4ac when I put it alphabetically. Next, I want to get rid of the a. Divide by a, or multiply by 1 over a. So on the right side, b squared minus 4ac over 4a squared. So next I'll square root, and I have to remember plus minus. X plus b over 2a equal to plus minus. I'm going to break the numerator and denominator apart from each other. So the numerator I can think of it as the square root of b squared minus 4ac. Sounds familiar. Over, when you square root the denominator, square root of 4 becomes 2, and square root of a squared becomes a. No square root anymore. It should not be, so this number right here should not be completely equivalent to this because this is out front. I had to multiply those two things together, and when I do, one of the a's cancels out of the bottom. To finish this problem off, one last step. Oh, I forgot it. Sorry, I just forgot the square right here. So now I subtract my b over 2a. We have common denominators, so I can make it one big fraction. So when I subtract the b over, it's negative b plus or minus the other numerator. Look what we have. We've solved for x. So x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Sounds like the lyrics to a wonderful song. That's your quadratic formula. That's where the quadratic formula comes from. That's why it's true. And now you can, on any quadratic, just plug in the numbers into this formula to get your answer. Subtracted b over 2a from that side. Subtracted b over 2a over here as well. Common denominator, so I wrote as one big fraction, so my numerator was that, all over 2a. What I'm going to do next, and the last thing we're going to take a look at today, is actually from the textbook. I'll project it up here. This is a summary. They call it the concept summary, actually. It's straight out of the textbook. It's page 269. But it summarizes all of the different methods that we've used to solve quadratic equations and when you can or when would be a good time to use it. First of all, we've identified already that graphing can't always be used, but sometimes it can. And the reason it can't always be used is because sometimes you don't have x-intercepts. Like when you have complex numbers, it's not going to show up on there. Factoring, same thing. Factoring can only be used sometimes. Square root property. We didn't really talk about square root property in terms of that name, but that's just when you can square root both sides of an equation to solve. We used it when we were completing the square, but the property itself can't always be used. Sometimes you can just square root both sides of an equation and solve and be done. That's why it's sometimes. But completing the square and quadratic formula are the two that can always be used. Then on the right side, they kind of give a summary of when each of these is the best thing to do. So graphing, they're recommending to use it if you don't need to know the exact answer. Sometimes graphing gives us the exact answers, but sometimes all we can get is decimals on our calculator, and that might not be exact. So if you don't need to know the exact answer, it could be useful. And it says there, it's best used just to check the reasonableness of your answer. So if you use a different method, you can graph it just to check and see if they're reasonable. Factoring says here, if the constant term is 0, or if it's easy to factor. So basically, if it's one that's easy to factor, I would use factoring. Doesn't always work though. Square root property, if you don't have a b term, or if you have a perfect square on one side. So if you have a perfect square equal to a constant, that would work. You may not have a number inside the parentheses there. That's okay. But you could use just square roots there. But completing the square can be used all of the time, but we prefer not to have a leading coefficient. So that's why they're saying x squared plus bx plus c, especially if the b is even. If you have no leading coefficient and your b is even, I prefer to use completing the square. Quadratic formula can always work, but it's a little clunky at times. It's not my favorite, and I know a lot of students make mistakes on the computation of it. But if you get a problem that doesn't have nice numbers, doesn't really fit into any of the other categories, then I would default to the quadratic formula. Some people like to use it for everything. I don't think that's always a great idea. It's not always a real efficient way to solve, especially if something's factorable, but it can be used for everything. So if you got problems that have decimals like this one, that's gonna be your go-to. So there's the summary of what to use and when. That's all I have for today. For notes,